Hello guys, this is Paul McWhorter with TopTechBoy.com, and we're here today with episode number 48 in our incredible new tutorial series where you are unleashing the power of your Raspberry Pi Pico W. What I will need you to do is pour yourself a nice tall glass of ice cold coffee. That would be straight up black coffee poured over ice. No sugar, no sweeteners, none needed. And as you're pouring your coffee, as always, I want to give a shout out to our friends over at Sunfounder. Sunfounder is actually sponsoring this most excellent series of video lessons. And in this class, we will be using the Kepler kit for Raspberry Pi Pico W. Now, most of you guys here at lesson number 48 probably already have your gear, but if you're one of the slow to order guys, look down in the description. There is a link over to Amazon. You can hop on over there and pick your kit up. And believe me, your life and my life are going to be a whole lot easier if we are working on identical hardware. But enough of this shameless self-promotion. Let's jump in and talk about what I am going to teach you today. And what I'm going to do is I'm going to show you my solution to the homework assignment that I gave you in lesson number 47. Now remember, where did we end up with in the last few lessons? Well, using the MPU6050 and using the 3 accelerometers on the 6050, we were able to create a little gadget that would measure a board. It would measure its pitch and it would measure its roll. So it would measure its tilt angle along 2 axes. It would sort of be like a carpenter's level, but instead of just looking in 1 axis, it would look in 2 axes. And we even came up with a cool little graphic on the OLED 1306 where we had a little bubble that was moving around in a reticle showing you what your tilt was, giving you kind of both quantitative and qualitative feedback. And so that was really a cool little project. But what was the problem that we found? The problem that we found is that we could very accurately measure tilt, but because we were measuring tilt using an accelerometer, if our device experienced vibration or if our device experienced deceleration or acceleration, it would interpret all of those things as tilt. So we have our nice accurate tilt measurement, and then we superimpose on top of that an error signal from either vibration or acceleration or deceleration. So what we worked on last week was we worked on removing that noise signal or mitigating that noise signal using our what? Our friend was who? Our friend was a low-pass filter. So we incorporated a low-pass filter so we could remove that vibrational error signal from our readings. Well, if we did that, why do we even need to go on? We could get rid of the error signal. But what was the challenge that we faced? We faced a trade-off between the more we squeezed out that error signal, the more sluggish our sensor became. So we could be very, very accurate and very, very low noise, but it was very slow to respond to tilt, or we could have it behave snappy in a snappy fashion, and then we would still have some of that noise in there. So we were trying to find that sweet spot in the middle where we got rid of most of the noise, but we were still snappy enough. So we had to make trade-offs. Well, we're engineers. Do we like trade-offs? No, we hate trade-offs. What do we want? We want something that is fast and stable. Okay, fast and stable. And that's what I'm going to kind of start working on today. The low-pass filter was a huge step forward. We'll probably keep using it as part of our solution. But what was the fundamental problem? The fundamental problem was we were measuring tilt using an accelerometer, and an accelerometer measures acceleration. It's kind of like a fundamental error that we built into our approach. Well, I ask you this, how do we go the next step? Well, I want you to think the MPU6050, we call it a what? A 6-axis IMU, or 6-axis inertial measurement unit, or a 6-axis MPU for motion processing unit, 6 axes. How many axes have we used? 3. We're looking at acceleration in X, acceleration in Y, and acceleration in Z. This bad boy has 3 other sensors that we're not using. It has an X-axis gyro, a Y-axis gyro, and a Z-axis gyro. Okay, there's 3 more sensors that we aren't using. The accelerometers measure what? They measure acceleration. The gyros measure what? They measure rotational velocity. How many degrees per second something is rotating about the x-axis, how many degrees per second something is rotating around the y-axis, and thirdly, how many degrees per second something is rotating about the z-axis. And that gives us new tools in our toolbox to make our little gadget work better. What do you want? Low noise and snappy. Okay, well, let me get out of your way. Let's talk about the accelerometer a little bit. We've got some fishermen out there working this afternoon. I love looking out the window and seeing the fishermen. But enough of this gazing off into the distance at fishermen. Let's come over to our sketch pad, okay? So now, what do we get from the gyros? What we get is a measurement of the velocity, the angular velocity. So it might tell us that we are rotating, and we've got 3 different numbers. We've got the velocity, the angular velocity about the x-axis. We have the angular velocity about the y-axis, and we've got the angular velocity about the z-axis, okay? What is angular velocity? Well, it is how fast something is rotating in degrees per second. So if I am rotating at 10 degrees per second for 1 second, how far did I go? Well, 10 degrees per second times 1 second would be 10. Or if I went 10 degrees per second for 2 seconds, I would have rotated 20 degrees, okay? Hopefully that makes sense. So these are all telling you about the axes, how many degrees per second you are spinning. Now, what I don't want to understand tilt, I don't want to know how fast it's rotating. I want to know what the angle is. Well, what is the angle? The angle is going to be the angular velocity times the time. Now, life would be easy if we were like a clock and just sitting there rotating at a constant rate, but that's not the way the real world works, right? We're rocking and rolling and we're moving around, and our angular velocity is not constant. So how do we calculate an angle in that case? Okay, well, let's say that this is the angular velocity, and understand you solved the problem 3 times. Once using the x-axis gyro, once using the y-axis gyro, and once using the z-axis gyro, okay? So if you do one, then the other 2 are just the same. You just swap out which gyro that you're using. But let's say that I am rotating at different angular velocities over time. Well, what we say is, how do we actually get the actual angle? Okay, and I can't just multiply it by time because it hasn't been at that velocity for the whole time. So what do I say? I say the new angle is equal to whatever the old angle was an instant ago plus the instantaneous velocity, okay, times not t, but delta t. That is the time between this measurement and the last measurement. So I make a measurement here, and I make a measurement here, and I make a measurement here, and I make a measurement here. Well, what theta is going to be is it's whatever theta we were at before, and then what do? I look at multiplying delta t, okay, that little tick in time, times my velocity. So it's this velocity times this time. And now I take another measurement, and then I do it again. I take where I was before, and then I add this times this. And so you're taking little bitty baby steps, little delta t's times your last velocity, and add it to what the angle was you were at before. And with that, then you can take the angular velocity that is changing and you can come up with your tilt angle over time. Does that make sense? I hope it does. Actually, what we did there, we just did a little calculus. I didn't want to tell you it was calculus because that would have scared you. One day I will show you how to do calculus, okay? But this is not that day. We're just going to jump back over here. And I think we're ready to actually start coding now. I think we're ready to start coding. You know, I think let me cheat a little bit. Let's come up here. I think we can get a quicker start if we come to the most excellent www.toptechboy.com, and we're going to look up the lesson measure pitch and roll with the MPU6050. Remember, this is the schematic that we're using so you can get things hooked up like us, and this was how we were measuring the tilt, using the accelerometer. But we're going to kind of cheat and take that, and then we're going to come over here. Let's see. Getting a little bit of a glitch there. Let me kill that. Sometimes Thonny gets a little cantankerous there, and I find the best thing is just turn it off and start over. Okay, so now I'm going to paste that code in. Doggone it. Let me try this again. This is not cooperating very well, is it? Okay, we're going to do it the old-fashioned way and just grab it like this. Sometimes it doesn't get that copyright from the website, and when it does, you can just do it like that. Okay, so now that works. This is just, let's just make sure that this works. This should just be giving me pitch and roll. This should be giving me pitch and roll just based on the accelerometers. And so let's try this and just see. I've got to hook up to the I guess I didn't get the first line of that when I copied it, so I'll add it up here. From IMU import MPU6050. So I'm having trouble copying and pasting today, and that's pretty sad, isn't it? Okay. 6050. Okay, there it is. Now, as let me make this full screen. Okay. As I roll, it's rolling. I'll show you here. As I roll, it's rolling and it's giving me accurate measurements. As I pitch, it pitches. Okay. And so if it's doing that, what's the problem, right? What's the problem? Well, the problem is that when I shake it, it's interpreting that vibration. It's interpreting that vibration as a tilt, as a roll or a pitch. Okay, so that's what we want to get rid of. So now we're going to kill this. Really, we just copied this program because it's got some stuff that's kind of useful in it. So we come up here, and this top part is setting things up. This is setting up our MPU6050. Yeah, we want to go ahead and say roll is 0, pitch is 0. And I also want to incorporate a new concept. Remember, this was pitch, positive pitch is up, negative pitch is nose down. Then I've got roll left and I've got roll right. So I've got pitch and I've got roll. But I want to introduce a new concept, and that is yaw. That's turning this direction. You can't measure yaw with an accelerometer, but you can approximate it with gyros. So we're going to get a little bit of data that we didn't have before. Okay, so what I'm going to do is I'm going to say roll is 0, pitch is 0, and I'm also going to set yaw equal to 0, like that. So we've got that thing all set up. And then what I'm also going to do is I'm going to come in here, and then instead of having x acceleration, I'm going to have x gyro. instead of y acceleration, I'm going to have y gyro. And instead of z acceleration, I'm going to have z gyro, like that. And then I'm going to have, instead of measuring MPU accel x, it's going to be MPU gyro x, MPU gyro y, and MPU gyro z. What is x gyro? It is the rotational velocity in degrees per second about the x-axis. What is y gyro? It is the rotational velocity in degrees per second about the y-axis. What is gyro? What is z gyro? That is the rotational velocity about the z-axis in degrees per second. Does that make sense? And so what I want to do is, I got to get rid of all of this nonsense here. Not much of that at all was very useful, was it? Okay, so let's get rid of all that. And then let's even get rid of this. But at least we're making the 3 measurements now. So let's go ahead and let's just print those 3 measurements. Okay, so what I'm going to do is I'm going to print just the raw data coming off. I'm going to print the raw data coming off, and that raw data is going to be x gyro, comma, that's going to be, let's put in a label x gyro, and then comma, x gyro, and then y gyro, comma, y gyro, and then comma, z gyro, comma, z gyro. So I should get 3 measurements, and I should see them coming out across my plotter here. So let's go ahead and run this and just see if I get data. What is this invalid syntax in line 18? What is this nonsense? Need a closing parenthesis. Now let's try it. Hey, I'm getting measurements. And let me kind of shake this around a little bit. So as it's sitting there, what is my rotational velocity? My rotational velocity is 0, 0, 0. Why? I am not rotating. Okay, now it is the green one is the rotation about the z-axis, and that's the yaw. Let me see if I give it some yaw if it sees a signal in the green. So I'm going to turn it, and what? It read counterclockwise is positive and clockwise is negative. Okay, clockwise is negative, counterclockwise is positive. And what do I see? Now what I want you to see is if I go from here to here, I see a signal. If I go from here to here, I see a signal, but it always goes back to 0. Why? I'm not measuring position, I am measuring velocity. How do I get position? By adding every little delta t times the last measurement. So I take the rotational velocity times the delta t since the last measurement, and I add to that the rotational velocity times the delta t since the last measurement, and then I should just be able to add up all these numbers, and I should be able to get what? The actual position, whether we're talking about pitch, roll, or yaw. Okay, is that pretty cool? I hope it is. So let's come in here, and what I have to do is, first of all, I need to create a stopwatch because I need to know how long it has been since my last measurement, and that's going to kind of be my loop time. So I need to start my stopwatch at the first of the loop, and I need to stop my stopwatch at the end of the loop. And I'm going to go ahead, and so it doesn't crash the first time, I'm going to just say the t loop. I'm just going to set the first one equal to 0 just because it has a value, it has a place to start. And then what I'm going to do, I'm going to start my stopwatch by saying t start is going to be equal to time dot ticks in milliseconds, like that. What does that give me? The number of milliseconds since the epoch. And that is not S start, that should be T start. Okay, so that starts it. And then I'm going to come down all the way to the bottom, and then I'm going to say T stop is equal to time dot time underscore time dot ticks underscore milliseconds, like that. Okay, and now T loop is going to be equal to T stop minus T start, like that. Now what you got to see is this is reporting in milliseconds, and we want to do our calculation in seconds. So we need to convert milliseconds to seconds, and we do that by multiplying by 0.001. And now what we should have is, this is, what is that? Got an extra one there. Okay. Now what is this going to do? That is going to be the time that it goes through the loop. That is our delta t. That's our little increment of time, which we multiply by the rotational velocity, and we add it to our last angle. Okay, so what are we going to do here? Let's do yaw first. Let's just see if we can do yaw. Okay, so I'm going to come up here, and yaw is about the what? It's about the z-axis. That's the one that we couldn't do before, right? The z-axis comes down like this, straight down, and we're rotating about z like that. And we couldn't do that with just the accelerometer. So let's come in, and now what am I going to say? I'm going to say yaw, which is an angle. That's how far I've rotated. That's an angle. Yaw is an angle rotated about that. Rotated like that. Okay, yaw is equal to the what? The old yaw plus my rotational velocity, which was z gyro, times what? Delta t. What is our delta t? T loop, the amount of time since the last measurement. Okay, now let's see if we can just print yaw like that. Could it really be that easy? Could it really be that easy? No, it's not quite that easy. Okay, it's not quite that easy. What you got to see is this is very, very dependent on accurately getting those measurements. And what we've got to see is that print statement. When we do print, that print statement is kind of a slow. That print statement is kind of a slow step. Okay, the print statement is kind of a slow step. And so what I want to do is I want to measure every time through the loop, but I don't want to print out every time through the loop. So I'm going to come up here and I'm going to create a counter, and I'm going to say count is equal to 0. And then I'm going to come down here, and what I'm going to do is right before I kind of do the whole do the whole calculation of the t loop, what I'm going to say is if count equal 50, then if count equal 50, what am I going to do? And I probably up here should increment the counter, CNT equals CNT plus 1, like that. So I increment the counter, and then I only want to print every 50th measurement. So if count is equal 50, then what I'm going to do is reset the counter, count equals 0, and then I'm going to print yaw. So I only print yaw every 50 measurements, and it's still going to be pretty darn fast. Okay, and why do I have the 0.05 here of sleep? Just so I'm not hammering that MPU6050 faster than it can make measurements, okay? So I'm going to need everyone to hold their breath. We're getting data, okay, and I want to give it a little bit of a read there. I'm doing it the wrong way. Let's just start over here. I was rotating the wrong way. I should have been yawing. Okay, so I'm going to start at 0, and then what I'm going to do is I'm going to yaw to 90, and then I'm going to yaw back to 0. Okay, so let's run this thing. Okay, starts at 0. I yaw to what? Minus 90. I yaw back, and it comes back to 0. Let's try it again. Okay, do you see that? I am measuring yaw. Okay, I am measuring yaw. Look at that. Boom! Giddy up. How cool is that? We couldn't measure yaw with the accelerometers, but now I'm measuring yaw. So what do we want to do? What do we want to do? We also want to measure pitch and roll. okay? And so we've made these measurements, but now we just got to convert them to roll, pitch, and yaw. So roll is going to be equal to roll plus roll is this way, and that is the y-axis, so that would be MPU.gyro.y. I sure hope I'm thinking about this right. And pitch is equal to pitch plus MPU.gyro.x, if I'm thinking about it right. So let's just see, and then what we're going to do is here we are going to print. We're going to print, I always think in terms of roll, pitch, and yaw, like that. And why do I define it? You see, to me, I'm thinking of this as an airplane. So this is the nose of the airplane. Pitch is like this, roll is like this, and yaw is like this. So I kind of have this mentally, an airplane in my mind, if that makes sense. Okay, so let's take a look at this. And what I'm going to do is I'm going to come in, and then I'm going to yaw. And look at that. I yawed just beautifully. Okay, now pitch. What? Okay, pitch is, am I doing pitch? Yeah, that was pitch. And now roll. There is something very disturbing here. Okay, this was a mistake even here. I should take that out. And I'm going to go, because I only want to print every 50th one. So I said I was printing every 50th one, but I was printing every time before. So now I'm going to print roll, pitch, and yaw, and I'm actually going to put labels in R, P, and yeah. The labels will help us because since we've got three, we want to kind of keep track of them like that. Okay, so now I'm going to try to make it where you can see more of what's going on. And then when I run this thing, wow, what is that crazy slow business? For some reason, it doesn't like every 50. What if I print every 10 times like that? Let's try that. That is still just crazy slow. What if I take the time.sleep out? Is there anything else that's slowing me up in here? Okay, I'm going to stop this. I don't know. I'm going to save this. Save as. And I'll save it as Gyro 2. Sometimes it's like that USB port gets confused and it goes real slow. And so let's just kill it and let's see if I can open Thonny again. Open, and it was Gyro 2. Okay, and let's see what happens this time. Okay, now it's going nice and fast. Okay, and so we got kind of a crazy value there on the roll, the pitch. The pitch, the orange is crazy. So let's see what's going on there. Roll, pitch, and yaw. And then we have X gyro, Y gyro, Z gyro. And we've got yeah, I see. I think that roll is MPU gyro. I forgot to multiply by the T loop times T loop. It worked on yaw, but then when I did pitch, I didn't put the times T loop in. Hopefully you guys saw that. Okay, so now yaw, pitch, and roll. And really what I need to do is, it would be better to use the measurements that I just made. I'm not exactly sure what I was thinking when I did that, but I wasn't thinking real clearly. So roll is about the y-axis, so that's going to be y gyro. And then pitch is going to be x gyro. Let's try that. I might still have a little glitch in here somewhere, but let's see what happens. Okay, we should now have this set up where we should be able to see roll, we should be able to see pitch, and we should be able to see yaw, all three axes. So I'm going to turn this, and I will then start by yawing and then pitching and then rolling and then see what happens. Okay, here we go. Are you ready? And you'll be watching the data and you'll be watching what my hand's doing. And so we're going to come in and I am going to run it, and then we are going to look at that. We are yawing, we are pitching, and we are rolling. Look at that. So you see I can go and it is tracking the position in all three axes. And so that is very good. Now what else do we like about this? Let me try this again. Okay, let me try this again. So I'm going to run it and then I am going to yaw. Look at that. I am yawing. I'm going to roll very nicely. I am going to pitch very nicely. Now watch, if I shake this thing, if I rotate it, shake it, yeah, I'll get some noise. But if I just do it linearly and not rotate it, what? I'm not getting any noise. And so what do I like about the gyro compared to the accelerometer? What I like about the gyro compared to the accelerometer is I don't have any noise due to vibration. Okay, what do I not like about the gyro? Now I was distracting you with everything moving, but what is something that you notice? What is something that you notice? Now the second one, the orange, is the pitch. That is this one, right? Okay, what is happening to that pitch value? Am I pitching right now? No, but the angle is slowly changing. I don't have a noise problem with the gyros, but I have a what? I have a drift problem. And let me show you that drift problem. I'll stop and watch. I'm not going to touch it because I don't touch it. It should sit and it should read what? A roll of 0 degrees, a pitch of 0 degrees, and a yaw of 0 degrees. But watch me run this, okay? Oh, look, it's 0. That's great. Oh, and what do we have on the orange? The pitch is what? Off to the races. And also the roll is off to the races. The green is off to the races. The orange is off to the races. Amazingly, what we see is that the Z, which is the yaw, it seems to be fairly stable, but I've got very large drift in that pitch. And in fact, the pitch seems to be drifting at about a degree a second. No noise, but a drift. What is the difference between drift and noise? Noise is something that's on top of the signal that's going up and down like that. That's noise. What is drift? Drift is when you're not moving and you're sitting and your values just drift off. And again, look at that. It's saying that I've moved this thing 180 degrees. It's saying that I did this with it when I didn't do that at all. Now, let's think back about tilt from the accelerometer. Lots of noise, but no drift, right? It would sit there with noise, but there was no drift at all. It was rock solid drift-wise, but it had noise. What about the gyro? It has no noise at all, but it has drift. What do I want? I want to measure tilt that doesn't have any noise, that doesn't have any drift, and is very snappy. So what do we need to do? We need to come up with a clever way of taking, not just do it with the accelerometers alone, not just do it with the gyros alone, but to somehow magically combine or fuse the data from the gyros and the accelerometer, and maybe even on the accelerometers throw in that low pass filter, and let's see if we can get something that is snappy and doesn't have noise and doesn't have drift. Okay, guys, man, I really hope that I am not making you all weary with all of these lessons on the MPU6050, but guys, I'm having a lot of fun with this. I am really having a lot of fun with it, and hopefully a few of you guys will be enjoying it as well. Okay, you know, that is going to be your homework assignment for next week. See if you can come up with a way of fusing the data from the accelerometer to the gyro to take the advantages of the accelerometer and combine them with the advantages of the gyro and get really clean signals out of that. Okay, guys, as always, I want to thank you all who are helping me out over at Patreon. YouTube's made it pretty clear that they don't love me or people like me anymore, and so really it's you guys that are helping out on Patreon. You're the ones that's keeping me in the game, and so I want to thank you for that. You all can also help me by giving me a thumbs up. It also helps if you leave a comment down below. If you haven't already, make sure you subscribe to the channel, and when you do, ring that bell so that you will get notifications when future lessons come out, and most importantly, share this video with other people, because the world needs more people doing coding and fewer people sitting around watching silly cat videos. Paul McWhorter with TopTechBoy.com. I will talk to you guys later.